Identifying the causes of disease and associations between factors involve comparison between groups of people who differ by exposure. This is the essence of epidemiology. In the second part of this lecture, we're going to review some of the most frequently used measures of association in epidemiology. Let's start by introducing 2x2 tables. These tables summarize the frequencies of diseases and exposures. You can use 2x2 tables to calculate measures of association and quantify the effect of an exposure on a particular outcome. Measures of association can be absolute or relative. Absolute measures subtract one frequency measure from another and give information about the public health impact of the exposure. Relative measures divide one frequency measure from another and give information about the strength of the relationship between an exposure and a disease. The formulas are simple. The key is to understand how we interpret absolute and relative measures. They both quantify the relationship between exposure and disease or outcomes, but they tell you something different about the association. Absolute measures can be risk or rate differences. The risk difference compares the incidence risk of an outcome in two populations. This is the risk in the exposed minus the risk in the non-exposed. It expresses the excess risk of disease associated with the exposure. On the other hand, the rate difference compares the incidence rate of an outcome in two populations. This is the rate in the exposed minus the rate in the non-exposed. It expresses the excess rate of disease associated with the exposure. For example, let's say we want to assess whether improved fitness is associated with decreased mortality. In this case, we're working with rates. We previously obtained the mortality rate in a group that was exposed to improved fitness and also the mortality rate of a group that was not exposed to improved fitness. After subtracting one value from the other to calculate the rate ratio, we find out that the effect of improved fitness was to decrease mortality by 54.4 per 100,000 person years. Let's see another example. In this one, we want to assess whether prone sleeping in babies increase the risk of sudden infant death syndrome. We have previously obtained the cumulative incidence or risk incidence between a group of babies who slept in a prone position versus a group who did not. We now calculate the risk difference between these two measures of risk, and now we can say that the excess of sudden infant death syndrome among babies who slept prone was 7 per 1,000 babies, or if sleeping prone causes SIDS, then 7 cases of SIDS per 1,000 babies could be eliminated if sleeping prone was prevented. We can also say that there is a 7% excess risk of SIDS among babies who sleep prone compared to babies who do not sleep prone. Risk differences provide information about how much of an outcome would be prevented if the exposure would be removed. This information is very useful from a public health perspective. Another term for risk difference is attributable risk, which is the excess risk due to an exposure. However, many discourage this use because it presumes a causal relationship between the exposure and the outcome. For the relative measures of association, let's start with the risk ratio. For the risk ratio, you simply divide the incidence risk in the exposed by the incidence risk in the non-exposed. The risk ratio is a measure of the strength of the association between exposure and outcome. It is often used in cohort studies and clinical trials to assess the excess in risk associated with an exposure, but in relative terms. We have again the 2x2 tables with the formula for the risk ratio. It is similar for the rate ratios, but remember that for risk ratios you use incidence risks and for rate ratios you use incidence rates. Let's suppose that you obtain a risk ratio of 4.2 from a prospective cohort study about the effects of smoking on the risk of developing chronic obstructive pulmonary disease, you will always be correct by saying those who smoked had 4.2 times the risk of developing COPD compared to those who did not smoke. Rate ratio compares the incidence rate of an outcome in the exposed group compared to the non-exposed group. Because the rate ratio compares rates, it's the only measure that takes into account the present time at risk in each exposure group. It's the preferred measure in cohort studies and clinical trials of common outcomes and in populations with a large number of people entering or leaving the study groups. You might have seen the term relative risk. For rare outcomes conducted in close populations, the risk and the rate are similar. In these circumstances, we can use either the risk or the rate ratio. Because of this, sometimes people do not make these distinctions and call them both relative risk. However, it's always better to specify which relative measure of effect you're using. In our example of improved fitness and mortality, we can calculate the effect in relative terms. We divide the mortality rate in the exposed group by that in the non-exposed group and say that the effect of improved fitness is to almost cut the rate of death in half. When the relative measure of effect is less than 1, the exposure has a protective effect. If the measure is equal to 1, there is no association between exposure and disease. An RR of 2, for example, would indicate 2 times the risk or rate of disease in the exposed compared to the non-exposed. We can also express the RR in terms of the percent relative effect by subtracting 1 from the risk ratio or the rate ratio. In this example, we subtract an RR of 1.6 from 1, and then we can say that the exposed group would have a 60% increased risk or rate in the outcome. Same here. If we have a rate ratio of 1.51, the excess relative rate or percent relative effect would be 51%. The odds ratio compares the odds of having the outcome in the exposed group with the odds of the outcome in the non-exposed. The odds ratio provides an estimate of the relative risk when the outcome is rare. It's used in cross-sectional studies, case control studies, and cohort studies. We can see here again our 2 by 2 table and the formula to calculate the odds ratio, which is the cross product of the cells in the table. Let's take a look at the results of a study that assessed whether exposure to folic acid during pregnancy reduced the incidence of neural tube defects in the baby. By calculating the cross product, we obtain an odds ratio of 0.29 and conclude that those exposed to folic acid during pregnancy had 0.29 times the risk of the non-exposed group for the development of neural tube defects in the baby. Folic acid has a protective effect on the incidence of neural tube defects. Measures of potential impact tell us how much of the disease burden will be reduced if the exposure is removed. They provide a measure of the public health importance of exposures, assuming that the exposures cause the outcome. They include the attributable fraction in exposed and the attributable fraction in the whole population. The attributable fraction in exposed cases is also known as the etiologic fraction. It measures the proportion of disease in the exposed that would have been eliminated if we eliminate the exposure. For example, if we obtain a risk ratio of lung cancer of 10.4 associated with moderate smoking, we can calculate the attributable fraction using the formula here and conclude that 90.4% of lung cancer in people exposed to moderate smoking would be averted if they had not smoked. The attributable fraction in the population estimates the burden of disease due to the exposure on the entire population and not just among the exposed. In this way, we can determine which exposures have the most relevance to the health of a community. The attributable fraction in a population is the proportion of disease in the study population that is due to exposure and that would be eliminated if we remove the exposure. It provides a measure of the public health impact of an exposure for the entire population. So we know how to calculate point estimates that summarize the magnitude of association with a single number that captures the frequencies in both groups. These points estimates, however, are subject to random error, and one can indicate the degree of precision in the estimates by computing confidence intervals around them. A 95 confidence interval means that if the same population were sampled on numerous occasions and confidence interval estimates were made on each occasion, the resulting intervals would contain the true population parameter in approximately 95% of the times. There are several methods for computing confidence intervals for measures of association. You will not have to learn these formulas. I'm just presenting them to you so you can see the components of the confidence interval. Finally, a few words on how to compare rates among different populations. You might have a crude rate calculated for one population, summarizing the actual number of observed events in the population. Specific rates provide this information for segments of the population divided by age or sex, for example. It's often difficult to make fair comparisons of crude measures of disease frequency because of key differences between the groups that affect disease rates. Therefore, we should adjust the rates, which means to standardize them to a control population. The new standardized rates will allow comparisons of event rates between populations when there are differences in the characteristics between the populations that might influence the event of interest. Standardization of rates can be done by direct or indirect methods. Direct methods apply rates from the study population to a standard population distribution to allow direct comparisons between the two populations. The indirect method applies rates from a standard population to the numbers of people in each group of the study population to calculate the expected number of events. You can obtain two standardized measures of association using indirect methods: the standardized incidence or morbidity ratios and the standardized mortality ratios. These measures will allow investigators to comment on how the observed frequency of disease relates to what would be expected based on the disease frequency in the standard population. In this lecture, we have reviewed the main measures of disease frequency and association in epidemiology. Following what Ben Goldacre says in his book Bad Science, it's important to watch out what the media says about studies and what studies published in journals say. Now you have more tools to identify how they define exposures, diseases, and what measures of frequency and association they use to report the results. In the next few lectures, you will learn how to appraise this body of literature. Next steps for this week include our quick trivia and case study exercise. Do not forget to post at least one comment in the weekly forum. Bye now.